All right, so 5 install mistakes that kill systems. 5 things, 5 large, wide categories of problems that kill systems, things that you don't set up properly. So this kind of goes into the 2 different elements of process in air conditioning and refrigeration. Almost everything we're going to talk about here applies to both air conditioning and refrigeration, more on the air conditioning side. But these are things that installers have to think about, both in the install practices, sort of the practical skills of installing an air conditioning or refrigeration system, and then also on the startup and commissioning side. So I want to focus more and more at HVAC school and at Kalos about the commissioning side. Once you get something started up, making sure that it's really operating the way that it's supposed to, because that initial part of the life of a unit is such a key part in the long-term efficiency, longevity, and capacity of the equipment. And those are really kind of the 3 legs of the stool that I always think of: efficiency, longevity, capacity. It's got to last a long time without problems. It's got to have the proper capacity, meaning the amount of cooling or heating to be able to do the job, and it needs to do it efficiently so that it's not costing an exorbitant amount of money or more than it's designed to. This is focused on the air conditioning side, air side, and cooling side. We're not talking about gas furnaces here. That's one thing that I often kind of lack in is we don't have as many gas furnaces in Florida, so I don't focus as much on gas furnaces. So this is more on the air conditioning side. But since we're here in the spring and where everybody's starting to come into cooling season, starting to think about cooling season, I thought it was a good time to talk about the 5 install mistakes that kill systems. This presentation was originally designed to be done throughout the state of Florida at Johnstone's, but then it got canceled. So I was supposed to be doing this class at Boynton Beach, and I figured, hey, we'll just share with everybody, Kalos folks and HVAC school folks. So these are the 5 things. 5 things are improper brazing, flaring, and leak testing, which we'll talk about, all of those elements. Failing to flow nitrogen and what that does to the system. Poor evacuation. We're not going to do the deep dive into evacuation that I've done a bunch of times, so let's just talk a little bit about it. No or improper airflow setup. In most cases, no airflow setup is what happens in the field. And compressor overheating and flooding. So these are my 5 faves when it comes to things that kill the system. All right, so let's talk about proper brazing, flaring, and leak prevention, best and worst practices. So having the proper amount of refrigerant in the system is super key to efficiency and operation. And a lot of techs or installers, when they start up a new system, they focus so much on making sure to dial that charge in. You'll hear that. I just want to make sure to dial that charge in. Whether if it's a TXV, they dial in the charge by subcooling. If it's a fixed orifice or piston system, they dial it in by superheat, and they can get super obsessive about that. I mean, and again, that's a good thing. It's good to care about dialing things in. But if you have a system that's not leak-free, it's not clean, dry, and tight, you're really chasing your tail, because you have to start with a system that's not going to leak in any significant amount. Now, before we go further on that topic, though, I have to say that every system leaks to some degree. And you know this if you do your deep micronic decay tests, meaning you pull down to a really deep vacuum and you check to see if it rises. You'll notice that they all rise. And that's because every assembly, whether it's your hoses that you connect to the system or flare fittings or the seals and chatla fittings or whatever, they do leak some. And mechanical fittings, meaning fittings that you're, twisting in place that have threads, those tend to leak more than brazed fittings, which is why if you want a really, really tight system, then you braze it in. And that's why most unitary manufacturers, that's why they have brazed connections versus other types of connections. To say there aren't some really great mechanical connections, but if you want to get it really, really tight, then brazing is the way to go, which is why we've done it that way since all of us can remember. So we do want to try to keep them leak-free, and let's talk about that. First thing, when brazing, let's talk about some of the worst practices, some of the things that people do wrong on the brazing side. So brazing without nitrogen. This is an image of copper tube, one brazed with nitrogen, one brazed without nitrogen. The difference between the two, pretty clear. Now, one thing that I always say whenever I show these sorts of images is that most of these are done with wide open tubing with pretty high heat. And so these are sort of worst case scenarios. It's not necessarily this bad inside the system if the system has had very little exposure to oxygen. So in order to build up this black stuff on the side of the copper that you see here, this is called cupric oxide or copper oxide. And the reason that happens is the presence of oxygen and the presence of high temperatures together inside the copper is what results in that or outside anywhere. You get it inside, outside, wherever, but it requires the presence of high temperature and it requires the presence of oxygen. So if you have some copper tubing that was sealed off from the factory and never left open, then you're not going to get quite this much. But when you braze on an open tube, this is what you will see. And all this cupric oxide is going to make its way into your valves, into your screens, into your filter dryers, and it's going to plug them up. We want to flow nitrogen in order to prevent that from occurring. Another brazing worst practice is sweating off joints. That means in order to pull things apart, you're heating them up to pull them apart. Now, on installs, you don't generally do that. So that's more of a service practice, but you really want to try to prevent from doing that. Whenever you have to take things apart, it's really better to cut them apart. And there's several reasons for that. One is there's a safety element to it. When you sweat off joints, sometimes they can kind of pop apart, oil can catch fire and that sort of thing. That's one reason. But another reason is that you're going to be more likely to release moisture back into the system, especially when you're working around things like filter dryers. Definitely want to cut out filter dryers. But in general, if you can prevent from having to sweat things apart, then cut them apart. Now, there are cases where you have close coupled valves, some compressors, whatever, where you don't have a choice but to sweat them apart. But in general, try not to do that. Next, brazing worst practice is sanding copper after it's been cut. That means that if you're going to use emery cloth, you're going to use a Scotch Brite pad, something like that, to clean your copper, which is a really good practice. You want to do that before you cut it. So an example would be if you are going to cut out a dryer, go ahead and sand it, go ahead and clean it first before you cut it, so that way you're not dropping little shards of copper. Because when you're sanding copper, when you're cleaning it, there's the little pieces of copper that are coming off, and you don't want that going into the system. Sand before you cut. Don't allow burrs to fall on the copper. This is another key thing. You see this a lot when technicians learn that they should deburr or ream their copper, which you should in all cases if you can do it safely. That's this edge that occurs around the copper after you cut it, because that cutting wheel digs into that copper as you're kind of running it around the tubing. You want to take that burr off because that burr impinges on the copper and it creates turbulence there. And we don't want turbulence inside the tubing. That leads to inefficiency. So you do want to remove that burr. But what I see a lot of cases is techs will deburr with the copper standing straight up, and they'll drop the burrs down into the copper. What I would suggest is that in most cases, if you can hold it sideways or tilt it down when you're deburring, that's great. If you can't, because of the position, then I would say it's probably better to not deburr than to allow copper fittings to drop into the tubing. Eric says, I started using the deburr tool that looks more like a pen. It gives you a nice curled piece that you can grab. Yeah, and then again, that's a skill thing. That's the one I prefer too. And I forget the brand, but it's just got a little hook on it, and you can kind of curl it off nice and easy. You're not kind of just sitting there and doing it real quick and dropping it down in the copper. And so that's a skill thing once you've gotten experience with it. And again, the message here is that you just want to make sure that you're not dropping it into the copper lines. It's better that you don't deburr than that you drop it in the copper lines if those are your choices. But it's better that you don't drop it into the lines and you deburr properly. Again, the term is often called reaming. So whatever you prefer to call it, reaming or deburring, either way works, but that does need to be part of your process. Another thing that technicians fail to do is failing to seal open tubing. This is more on the install side. If you're doing a rough-in stage and you run copper, you need to make sure that copper is completely sealed. And even if in Florida, for example, we run a lot of copper in chase pipes. So a lot of soft copper in PVC chases. I tell technicians, don't just use the caps or the rubber plugs that come in that copper when you run it, because you can easily damage and deform the end of the tubing, and then contaminants, air, moisture can get into the tubing. So if you're going to run through a chase, or you're going to be pushing copper like we do in Florida, pinch that copper, braze it shut before you even do that to make sure that you're not going to get anything in the tubing. So many times the kind of the nerdy technician types focus on things like evacuation and airflow testing and all that, but then miss the fundamentals like making sure that your copper stays sealed, even to the extent that when you're working with tubing. So if you're out in the field and you're installing a compressor, you're installing an evaporator coil, when you're in between steps, use a little bit of painter's tape even, just to block off the ends, just to make sure that you're kind of reducing the amount of moisture, air, stuff that's getting in there. Again, painter's tape isn't going to be completely sealed, but just as sort of a temporary measure while you're working to keep it sealed off. Just keep the open tubing sealed best you can. And if you're going to leave it for a while, make sure that it's sealed with brazed off and pressurized with nitrogen, which is a good practice anyway. If you're going to leave a house at rough stage, make sure to repressurize. braze off, put a Schrader port in the end, leave it under nitrogen pressure. On that note, I guess this is worth saying that versus just pressurizing, it's better if you can flow nitrogen through it. So force some nitrogen through it and then pressurize versus just pressurizing. And what that does is it helps displace any air that's gotten in before you pressurize, because if air has gotten in and you pressurize, you can still potentially have some condensation inside the lines. And so you do want to try to displace that air and oxygen before you pressurize. And that's just a best practice in general. All right, so next thing is don't move the torch too much. That's a brazing worst practice. We're going to talk a little bit more about that. Failing to draw alloy into the joint, so failing to use enough heat on the joint. This is the biggest mistake that I see. We'll talk more about this, but newer technicians, they are afraid of burning things up. So what do? They start moving the torch all around and they don't use enough heat and they don't draw it into the joint quick enough. And so most often, newer techs, newer installers will burn up valves. Well, one, because they don't protect the valves, but two, because they are taking too long, not because they're using too much heat. Most often, I see newer technicians failing to use enough heat. And it depends on the person. You'll see some people get in there real aggressive and they'll burn right through the copper. But that's actually more rare. Most people, when they get a torch in their hand, they want to start moving it around and they don't use enough heat versus using too much. And the next thing is overheating valves, burning finishes, and wires, which just requires a little bit of forethought and protecting the valves and the different components. So let's talk about, we're going to talk only about copper to copper brazing here. I talk a lot about different types of metals and all that sort of thing, but we're talking install practices here. So let's be practical. When you are heating a joint for installation, and we're going to say that most of you are probably using an oxyacetylene torch. Some may be using air-acetylene or swirl, turbo torch type of flame, which is totally fine. There are some different practices, but the goal here is to get the base material to 1200 to 1300 degrees. So you want to get the entire joint between 1200 and 1300 degrees. So that is between dark cherry and medium cherry. That is the temperature change or the color change that you want to see on that copper before you begin applying rod. And the easiest thing to do is just to get your torch up to it. And then if it starts to get a lighter color than dark cherry, then just back the torch up a little bit. As you braze, just kind of move the torch around, allowing the base metal to melt the rod. I don't think brazing is really that complicated, especially with copper to copper. But the biggest mistake I see people make is not getting the entire joint to that dark cherry to medium cherry color before they start applying the rod. Some will say, well, you don't actually have to get it that hot. Well, there are some rods out there that will melt more in between the blood red and the dark cherry temperature, really high silver content rods, that sort of thing. But in general, most of the rods that you're going to be working with, you're going to require you to get to that temperature because that's the temperature that your rod melts at. There's these two different points called liquidus and solidus, and that's because your rod has multiple components in it. There's multiple materials inside of a rod. Most of the rods rods we use are 15% silver. That's a really good quality rod to use, but then it also has phosphorus and copper in the rod. And so you have these different metals that all have to melt in order to pull into the joint. If you don't heat it up enough, some of the metals will melt, specifically like the silver will start to melt first, but you're not going to draw it into the joint with all of the metals in order to have that proper bond. A lot of technicians out there, a lot of installers get used to just heating up the edge of the joint, thinking that is enough, and it will often seal in a lot of cases. So it won't necessarily leak right away, but then over time, you'll get these little tiny pinhole leaks that are hard to find. And it's just because rather than pulling into the joint, they've just sealed the edge. And we've all seen that. Next thing is, and this comes down to the concept of oxidization. I actually wrote a tech tip about this yesterday. The type of flame you want to use is a carbonizing or a neutral flame, which means that you either have this small third feather. So the way I look at it is you've got second feather. You've got your first kind of flame here, you got your second feather, and then you have your big feather that goes out here on the oxyacetylene. It's calling it here the acetylene feather. You want to have a slight carbonizing flame, also called a reducing flame, or you want to have a neutral flame, which means you just make that feather disappear. You do not want to have an oxidizing flame. And the reason is an oxidizing flame has excess oxygen and it oxidizes the joint. And so it creates oxides, copper oxides, cupric oxide, and that results in a weaker bond, a weaker joint connection. You want to have one of these two types of flames. My preference would be that you use just a slightly carbonizing flame, otherwise known as a reducing flame. As I'm going along, if you have any questions, feel free to ask them in chat. Okay, so now we're going to talk about brazing best practices. You want to braze while flowing nitrogen at 3 to 5 SCFH. The S just means standard cubic feet per hour. So really CFH is a better way of thinking of it. I've heard people say 3 to 5 PSI. Nope. You do not want to pressurize while you are brazing. You want to flow. So flowing and pressurizing are two different things. And 3 to 5 SCFH is just a whisper of nitrogen. A lot of guys will say, well, I don't have a special nitrogen regulator. Well, first off, they're not that expensive. You can get them. You can get the nitrogen regulators that have flow built in, or you can get a separate little nitrogen regulator that has the floating ball for this purpose. But if you don't have either of those, what you do is you just take the T handle on your nitrogen regulator and you just adjust it till it's just barely whispering. That's not a flow regulator, that's a pressure regulator. So that's not ideal, but it'll work in a pinch. And we do it all the time. So what I don't want technicians to do is use excuses for not following best practices because they claim they don't have the proper tools. Because in a lot of cases, there are really effective workarounds like that you can still flow nitrogen while you're brazing. It's not that difficult. You have to pull the nitrogen off your truck anyway. And it's going to prevent a lot of problems down the road, especially with things like TXV failure. You just flow nitrogen. A lot of people will say, well, how do you flow nitrogen? Well, you hook it up to your nitrogen tank and you open up the other end and you just flow it through. Now, sometimes that last joint may be tough to get sealed. And if that is the case, then if you need to shut it off for that last joint, well, then that's fine. Because again, the goal is to have displaced as much of that air and oxygen as possible, because it's really the oxygen and the water vapor that are our enemies inside the system. Oxygen and water vapor are in our air at all times. So by using dry nitrogen, we displace that. Bert says there's a great video on HVAC School for how to flow. Yes, Bert has a video up on the HVAC School YouTube channel on how to flow nitrogen while brazing. And in fact, even before you flow, like we said, you need to purge first, because you have to get all of that air displaced before you even start to flow nitrogen. So purge it through first and then flow. Next thing is when you're brazing, wear proper PPE. That means definitely wear safety glasses, masks, those sorts of things. There is a recommendation by OSHA that you should use, I think it's called a class 3 darkened lenses, because there is actually some radiation that comes off of even an oxyacetylene flame. So if you're going to be doing a lot of brazing, that's something you're going to want to talk to your manager about, wearing a tinted, properly specified safety glasses for that. And it's a good idea to wear gloves, although it seems like most people in our trade don't wear gloves. Of the two, it's far more important to make sure that you're wearing eye protection. Like we mentioned, don't cut joints rather than unsweating them. Sand copper before it's been cut. Deburr only when safe to do so, meaning that deburring is important, but only do it when you're not going to drop crap in the lines. Always seal and cap tubing when transporting or leaving. Allow the copper to melt the alloy, not the flame, which means you got to get the copper to the right temperature, and protect the work area and components. And this work area and components part is an important one. I would always suggest having a fire-resistant drop cloth. That's a big one if you're going to be brazing inside. So you lay down that fire-resistant drop cloth. It's like made out of a fiberglass sort of material. You lay that down underneath where you're going to be brazing to protect carpet and vinyl flooring or anything like that. Even better yet, if you're dropping little bits of braze material that can even burn through that, is take a piece of sheet metal and lay that down. Think about if you're going to be brazing up near a wall, for example, especially with air-acetylene. So if you're using an air-acetylene rig rather than an oxyacetylene rig, air-acetylene is a cooler flame, but it's a bigger flame, and it projects more convective heat. And so you want to really think about protecting what's behind it. If there's wires or any sort of painted surfaces on the other side, get those out of the way if you can, or protect them with a metal heat shield. You can also use, there's a lot of different gel sprays. Those gel sprays are really nice for spraying on surfaces that are kind of in the zone where they could get damaged by some of that radiant or convective heat. Just spray those down with the gel. I've seen people use gel on things like valves, next to the brazing area. That generally doesn't work. Your best bet there is to, get a wet rag, or get wet rag, or hot block, or, one of those other products that putties that you can pack around the valve. Those work probably the best out there, because then you can pull them off and reuse them when you're done. Mo says gel is nice for brazing inside units with insulation. Right. And I think you were telling me about this the other day, Mo. Somebody was. I think it was you. Actually, maybe it was my tech, Travis, I think was talking about it too, that whenever you have cases where you're brazing, inside and there's insulation, just making sure to get that all kind of soaked or at least coated with some sort of a gel to make sure that you're not scorching it, because scorching of insulation happens a lot. So think about all those things. Now, this image here is one that I've had out for a while. And this is some of this is disputed ground. Techs get really worked up about where you heat first and where you heat second. But this comes from essentially Harris's guidelines, where they say heat the tube first, and then that conducts heat into the joint, and then move the flame around over the joint. Again, you're not wiggling it all over the place, but you're just kind of moving it around in order to get it to the proper temperature, which is that dark cherry red, and then apply heat to the joint edge without melting the alloy directly with the torch. So this looks like I'm heating it directly with the torch, but it's because it's in 2 dimensions. Draw the alloy all the way into the joint. So I tend to finish by heating up deeper into the joint itself to make sure that it's drawn in. And then often I'll come back up to the top and just sort of put a nice cap on it just so it looks pretty. Inspect with a mirror and then allow to cool naturally before wiping clean with a wet rag or brush. I do like wiping it clean just so that way you can better see. It just, it looks nicer at the end. But I would definitely allow it to cool naturally, which is different than soft soldering. A lot of plumbers, soft solder, they'll actually tell you to cool it right away. And that actually makes for a stronger joint. I was just reading that the other day, which I'm not an expert at soft soldering. But I think that may be where some of that quenching sort of action comes from, where people are wanting to cool it off right away. But you do want to let it cool down. Now, you don't want to let it cool. You don't need to let it cool all the way to ambient. Just let it cool down, 500 degrees, something like that. Just, give it a couple minutes. You don't need to let it sit there all day long. Next thing here is using a torque wrench when flaring. We're just talking about flaring in general, but the first thing here is use a torque wrench. And the reason why, more than anything else, why I would suggest that you use a torque wrench for a while at least while flaring. Now, again, you should do it all the time, but just being realistic here is because a lot of people don't realize that it requires different torque specs for larger copper versus smaller copper. So if you look at like a ductless system, this is the most common case in air conditioning where we're still using flares. The larger diameter, so maybe your 5/8 or your 3/8, need to be tightened to a much higher spec than the 1/4 inch does. We don't think about that, and we tend to kind of tighten everything to the same tension. But if you look at the spec and you use a torque wrench, you'll get a much better feel for what that feels like. And what you'll find is that often the larger flares need to be tightened much more than you're used to, and the smaller flares need to be tightened less than you're used to. Because either way, you can create damage if you over or underdo it. If you underdo it, you're going to potentially leave leaks. It's going to be more likely to begin to leak over time if it's not tight enough. And if you overdo it, you can actually smash the flare, and then it can potentially leak for that reason as well. So use a torque wrench, get a torque wrench out. If you don't have one, you can get one. There's a lot of different ways you can do it. My favorite torque wrench is not a digital. Yellow Jacket makes one that's an old school analog torque wrench that uses different heads that are sized specifically for common flare sizes. And that is my favorite kit because of the size of the heads. A lot of them are using adjustable crescent wrench style heads nowadays, like the one shown here in this poor image. I don't prefer those personally, but I understand why a lot of people like them, because you just have one and you can use it for all the different applications without having to change heads. But the biggest causes of flaring leaks that I see are improper depth is a big one. So not having the copper the right height above the block. And this is one reason why I strongly suggest just getting a modern flaring tool unless you've done a lot of flares. If you've done a lot of flares and you know how to make them where they don't leak, then you don't need to be listening to this part anyway. For newer technicians, a lot of them do struggle, newer installers struggle with making consistent flares, and it's because they don't have a feel for it. It's just one of those things that takes a lot of practice to get good at, and installers often just don't have that many reps on it, especially since there's only certain types of equipment that have flares. So I would suggest getting a good quality modern flaring tool that has a stop on it, so that way they run it through the block, it hits the stop, they know it's the right depth, and then you're good to go as far as that depth side goes. The next part is that forgetting to ream. Now, reaming deburring, it's a correct name for that. Reaming or deburring is really important when you're making a flare, and it's really important that you don't overdo it or underdo it. What I often see if I hand someone a deburring tool is that they'll sit there and they'll thin that edge out till it's almost like a little point, a little knife edge. And then when you try to make a flare with that, it will crack on the edges. And so that won't work. But if you leave that burr there, then it's not going to seal as well, because there's going to be a little burr left on the face of the flare. So either way, reaming, deburring is really important on flares. Obviously, cross-threading is something that you see a lot of newer installers do. And I think just practicing, taking that flare, assembling it, so taking the actual flare, pushing it up against that mating surface, that cone, lightly tightening it, that's the right way to do it. Where you see a lot of newer installers and technicians, they'll take the flare nut and they'll just sort of, immediately put it on the threads and start tightening it without actually pushing those two surfaces together. And that just comes from things that you learn when you're a kid working with your dad or with your parent, and they kind of show you how to prevent from cross-threading. But you'd be surprised how many newer workers just don't have a sense of that, and they have to be shown even things basically, basic ideas like that. Next thing is, don't over and under tighten like we talked about, and that's where using a torque wrench will give you a much better sense of that. Especially with newer installers, I definitely want to see them using that torque wrench so they can get that feel. And then improper use of thread sealant. So I'm a big fan of Nylog. We talk about Nylog a lot, and Nylog is designed to be used a little dab on it. Some people will say, well, you put it on the back of the flare, put it on the front of the flare, put it on the mating surfaces, put it on the threads. Frankly, I put a little bit on all of those areas, but we're only talking a little tiny bit. We're not globbing it on there. I put a little bit on the threads. I put a little bit on the mating surfaces where they push together. I put a little bit on the back of the flare. When I'm actually making a flare, in all honesty, I don't use Nylog when I'm making the flare. I still just use good old mineral oil, just a drop of mineral oil. And the reason is that Nylog is very sticky because it does actually act as a thread sealant in addition to an assembly lubricant, which is what makes it so awesome, especially under vacuum. It just helps you hold those really tiny leaks that can occur under vacuum. And that's actually one of the really big values of Nylog. But because the stuff is so sticky, I don't want to use too much of it. I don't want to go getting it into the system where I don't need to, and I don't want to get it all over my tools. So I'll actually use oil when I'm making it, just a slight amount of oil. And then when I go to put it together, I just put little tiny drops of Nylog on just to kind of make sure that everything seals together, goes together nice and snug. Now, one thing to mention there is that will change your torque spec. So what I say is most manufacturers will give you a torque spec range. I would not go to the tighter range. I would stay on the looser side because you can easily over tighten when you use an assembly lubricant like Nylog. And that is a feel thing because the spec's not going to tell you. And that's actually one argument that people will use for not using it. I'm just going on my experience, and my experience shows me that using Nylog greatly reduces flare leaks in the field. By deploying that into the field, we've seen much fewer flare leaks, and we've never had an issue of contamination, because that's the other argument. They'll say, you get that in the lines, it's going to plug up external expansion valves or electronic expansion valves. It's going to plug up the system. And we've literally never had that happen. My experience tells me that as long as it's properly applied, it will do no damage because it's made of refrigerant oil. Well, here we go. I already talked about all this, but I guess I need to know my slides a little better. Using a little bit of Nylog prevents a lot of problems. Don't use too much for a lot of reasons, but the main reason is that it's sticky and it'll catch dirt. So you don't want to use more than you need. Use a torque wrench, proper assembly lubricant, check flare against cone, use a modern flaring tool. Leak detection. So far what we've talked about is preventing leaks. That's a big one. When you have a system that leaks, it causes significant system impacts. All right, leak detection before test. First, purge before pressurizing. So you want to force some nitrogen through the system, make sure that it's moved through the lines and that you're displacing before you pressurize. Because once you pressurize, you can actually condense moisture inside the system by pressurizing. So you want to try to purge through first and displace as much of that water vapor and oxygen out of the system, air out of the system, atmosphere out of the system before you pressure test. And again, flow nitrogen while brazing as well. Pressure test at low side test pressure. Now, again, because we're talking about install practices here. When you're doing an install, you're generally going to be pressurizing the line set and the evaporator coil. So look at that low side test pressure spec on the equipment and pressure test at that low side test pressure spec. Often, I'll see technicians pressurize at much lower pressures than they should be. And in fact, I was guilty of this for most of my career. Most of my career, I pressure tested at 100 PSI. The problem with that is that when you pressurize at lower pressure than the specified test pressure, it's going to take you much longer to find leaks, and you're going to be more likely to have leaks at the end of the day. So if your low side test pressure allows you to pressurize to 350, well, then pressurize it to 350. That's going to be a best practice for pressurization. Allow to hold for at least 20 minutes. I know that's asking a lot. Some people want to do less than that, but the reality is even 20 minutes is a little too short. I mean, it would be better if you could do pressure tests for hours. Some manufacturers specify 24-hour, 48-hour pressure tests on things like VRF systems, VRV systems. You do want to hold it under nitrogen pressure for as long as you can, and recognize that, again, Every system is going to leak a little bit, but under standard nitrogen pressurization, it should be almost unnoticeable. If after 20 minutes you have a 1 psi pressure drop, that's a problem. You got to find out where that leak is. And it may very well be in your gauges, which is why I suggest not using complicated gauge manifolds for pressurization. I suggest using very simple probe type setups in order to reduce potential leak points. Electronic leak detection worst practices. So let's talk about an electronic leak detector and when to pull it out. First off, electronic leak detector is only going to react with what it's designed to react with, which is generally a refrigerant. And so newer people may not understand that you can't use an electronic leak detector with nitrogen. Nitrogen is present in all of our air. It's the primary constituent, primary thing that our air is made up of. You can't do nitrogen leak detection with any sort of typical leak detector because it's all over the place. So if you're going to use an electronic leak detector, you have to have refrigerant in the system, which is where if you had a system, for example, that was, had leaked down and you were having a hard time finding it, you could use a little bit of trace refrigerant and then pressurize on top of that in order to attempt to find a leak. That can be done, and that is okay by EPA standards. But in most cases, if you have a really big leak, you're going to be best using your ears, using a bubble solution in order to find that. If you want to learn more about leak detection, I would suggest going to the Refrigeration Technologies site and looking at their guide on leak detection, because it's a really good one. Kind of goes step by step through, where to start with leak detection. But as far as using an electronic leak detector, first thing is most guys move too fast. You're not going to just go in there and wave it around and find a leak. If you're doing it on an evaporator coil or on tubing or whatever, you need to move very, very slowly. Some technicians forget the difference between a heated diode and infrared. So if you're using a leak detector that's a leak detector you're not familiar with, you need to know, is it heated diode, heated pentode, one of those sorts of leak detectors, or is it an infrared leak detector? These are by far two most common types. And the big difference is with a heated diode, heated pentode type, you can take it and place it right on the leak and it'll just keep going off as long as it's over the leak. Pull it away, it'll stop. Move it back in, it will pick up the leak again. With infrared, you have to keep moving it. So if you move an infrared over a leak, it'll go off. If you hold it there, it'll stop going off. So you have to keep passing over the area very slowly. In both of them, you can't move too fast. So moving too fast is a problem with every type of leak detector. But with an infrared, you have to always move it, because what will happen is if you're used to heated diode and the way it works, and you try to do the same thing with infrared, where you take it and then now you hold it over the leak, it's going to stop going off and you're going to think, well, there's no leak there. So that's an important thing to know. Also, make sure you're using a quality electronic leak detector. The best leak detectors on the market are expensive. So that's a good indication of whether or not it's a good leak detector. I don't know any cheap, high quality leak detectors. A lot of good ones out there. My favorite is the Hvac H10 series, H10 Pro. Some people don't like the fact that it's kind of big and bulky. This one shown here is the Inficon Stratus, which is probably the highest quality handheld leak detector that exists. It actually show refrigerant concentrations in ppm, but it is in parts per million, but it is a infrared. So you got to get used to infrared if you're going to be using one like this. Fieldpiece makes a couple great leak detectors. Testo makes a great leak detector. I've tested all of those. They all work fine. The TIFF ZX1 is a handheld leak detector that has a great reputation in the grocery refrigeration space. So there's some good ones out there, but you don't want to go with cheap. They're going to cost you generally over about $300 to get a good leak detector, and that's on the low side even there. Expect to pay that for a good leak detector. Another mistake that people will do is they'll use an electronic leak detector with the indoor fan running. In order to do a proper leak detection, you want to do it in very still conditions with very little interference. And so when you're doing it with the fan running, obviously it's not going to work. It's gotta be off. It's got to be still. It needs to have been off really for a while. I also see this happen. People will use electronic leak detection outside, and they'll think that they have leaks all on their condenser coil. And the reason is that their gauges and ports are leaking, and that refrigerant is kind of moving around. Because remember, most refrigerants are going to be heavier than air, so they're going to settle around that condensing unit, and so they're going to get picked up all over the place because you connected and disconnected your probes, or because they're potentially still leaking. A lot of people use pretty leaky gauges, and that will create interference. And I can't stand false hits on equipment that are a result of a technician being sloppy with refrigerant that's escaped from the system. Another thing is don't forget to wipe off bubbles before electronic testing. A lot of times you guys will first try bubbles, and then if that doesn't work, then they'll go to electronic. There are some bubbles that cross interfere with some detectors, and so you want to make sure to wipe off those bubbles before you start leak detecting, unless you know that the bubbles that you're using do not cross interfere with your particular leak detector. I haven't had that experience with true blue bubbles in my leak detector. I don't find that they cross interfere, but maybe I'm wrong. So I'll leave that up to you to decide. Best leak detection, move slowly. Use liquid detector to pinpoint leak spots. Good old Big Blue. That's what we use at Kalos, what I've used for a really long time. I'm a big fan of using your ears, using your eyes. So listen for leaks, look for oil. If you see signs of oil, then grab those soap bubbles and spray it on there. Now, even finding bubble leaks, really small ones, is a skill, an acquired skill, because it requires a lot of patience. It's not like every leak makes these gigantic bubbles. Little tiny micro leaks make little tiny micro bubbles, and you have to get used to spotting those. There's lots of videos online. Bert's very proud of how good he is at finding those, and it is. It's a talent of itself. But always be looking for oil, always be listening, and use those soap bubbles to find them. Search with the system off when possible. One thing we do a lot on heat pumps, if we're trying to find evaporator coil leaks, is we will run them in heat mode for a little while just to build up the pressure and temperature of the coil to make it a little easier to find at the evaporator. So you can do that, but you still want to do your search with the system off. Remember to check your service ports. Remember that you connecting to and from the system probably caused some leakage there, so don't allow that to cross-interfere. Ventilate the area as needed in order to make sure that you're not cross-interfering. I've even seen people use a leaf blower just to kind of blow the refrigerant out of the area to help with leak detection, so it's diluted. And then never stop after you found one leak. There could be more. Just the other day, Bert did a post where he was showing that he found an obvious leak outside, but then in the process, his helper actually found another leak inside of the evaporator coil. If he would have stopped at the first leak, which in this case was actually the outside leak, he wouldn't have found the leaking evaporator coil. Proper evacuation, best and worst practices. So first, let's talk about what are we doing with evacuation? What are we trying to accomplish? I'm not going to get into the science of this too much here in this webinar, because we do a full version of this that takes an hour and a half by itself. But what we're doing is we're getting air out of the inside of the system. It's just as simple as that. And in order to get air out of the inside of the system, we have to create a low pressure zone at our pump in order to get all the stuff from the inside, or you don't get all of it, but as much of it as you can from inside the system, out of the system. That's our goal. And in order for us to do that, we have to use a micron gauge. So if you don't have a micron gauge, that's where you need to start, because none of this makes any sense if you don't have one, and if it doesn't actually work, and if you don't have batteries for it. So start there. Get a micron gauge, keep some rubbing alcohol in your truck so you can clean out the sensor if that becomes an issue. Keep some extra batteries for your micron gauge in your truck, and now you're going to be prepared to at least know if you have a good vacuum or not. And then you can decide whether or not you need to invest in some additional tools in order to do a good job. But this is our standard rig here. What you're seeing here is our standard setup that we use at Kalos. One hose, 1 3/4 inch hose, cores removed. This is a core remover here. Micron gauge on the liquid line, pulling only from the suction line with a good quality pump. And here we show a Hvac electronic digital pump. Electronic being the internal electronic micron gauge, and then it has a DC motor in it. So it's a really nice, high-quality pump. There's a lot of them out there. Another one of my favorites is the VP85 from Fieldpiece. This pump and the VP85 from Fieldpiece are my two favorite pumps on the market right now. But anyway, so this is our standard setup that we use at Kalos, and it works great. What are some of the worst practices? Well, some of the worst practices are skipping the micron gauge. Without a micron gauge, you have no idea whether you have a deep vacuum. It's just as simple as that. A lot of people will say, well, I just look at my suction gauge and see if it's all the way down. And I say, okay, that's great. That's like trying to measure off 10 feet with the odometer in your car. You can measure distance with the odometer in your car, but it measures at a scale that's completely unrealistic for measuring out 10 feet. And so a micron gauge has to measure this really, really fine level of vacuum, this really fine level of pressure that you're just not going to be able to do with a regular suction gauge on your gauge manifold. It's not going to tell you enough. The next thing that people do is they pull a vacuum through a manifold. And again, can you pull a good vacuum through a manifold? You can. Time consuming, and you're relying on the fact that your manifold isn't leaking. And most manifolds do leak, especially when you're measuring down and deep vacuum. So what I would suggest is not pulling through a manifold, and instead just connecting your vacuum hose directly to the system through a core tool. And you can use the core tool as your isolation. It just simplifies things and eliminates a lot of potential leaks that can wreak havoc on pulling a good vacuum. The next thing is people neglect to remove Schrader cores. Pulling Schrader cores is a really good practice for a lot of reasons. As part of installation, you really should be pulling Schrader cores initially when you're brazing anyway, to prevent from melting them while you're brazing the system in. So they should really almost, in most cases, they're already going to be out. Then you just put the core tool on, so that way you can put the core in again later once you've actually introduced refrigerant into the system. Removing Schrader cores should just be sort of a given, but the question isn't whether or not you remove them, it's when you put them back in. And I suggest that you don't put them back in until the system is actually charged and you're ready to run it. Then you can put the Schrader cores back in. That's also good practice, by the way, when you're recovering. So pulling Schrader cores is also very helpful for recovery. It allows you to get the refrigerant out of the system much quicker without having so much heat and having to recondense the refrigerant into the tank. Another worst practice is people leaving the pump open to atmosphere when not in use. So when you're not using the pump, you should shut it off. Put the caps back on. So it helps prevent that oil from being exposed to atmosphere when it's not in use. And then using refrigerant hoses for evacuation. We talk about this a lot, but refrigerant hoses, you're using them for charging, you're using them for recovery, you're using them for a lot of different things, and they can easily become full of oil and all sorts of stuff that you don't want to be getting in the way of the process when you're pulling a vacuum, as well as the fact that they tend to be more leaky and smaller gauge. So we suggest using large gauge dedicated vacuum hoses for evacuation, because evacuation can take a long time sometimes, and we want to make it as quick as possible to pull as deep as possible to ensure that you don't have any leaks. So use dedicated hoses. Proper pump maintenance, that means change your oil regularly. If you just connect a micron gauge to the pump itself, just micron gauge to pump, you should pull down to under 50 microns. If you do not, then you need to change the pump oil, try it again. Sometimes it takes a couple oil changes on a pump in order to get all that contaminated oil out of the sump of the pump, but make sure that your pump can pull below 50 microns by itself, just pump and micron gauge. That's a really good first test. Do that regularly to make sure your pump's performing. Remove Schrader cores like we talked about, and connect the micron gauge at the furthest point of the system, not the pump. So this is what we show here, is that this vacuum pump actually has a built-in micron gauge. And that's helpful because it tells you what the vacuum is at the pump, but it doesn't tell you what the vacuum is at the other side of the system. And that's why we connect our micron gauge on the far side, completely opposite from where you're pulling. Now, this is for install. This is for a typical install where you're pulling on a line set and an evaporator coil. If I was going to pull on the entire system, say I replaced a compressor or something like that, I would then use a T here and two hoses, and that way I would get more capacity. But at that point, then we'd have to use two core remover tools. We'd have to valve them both off when it was time to do our decay test, once we'd pulled down to deep vacuum. And then this micron gauge is going to be more prone to jump up. With this system here, once I pull to where this micron gauge says 300 microns and I valve off the valve here to see how quickly it rises, this valve isn't going to jump up quickly. In fact, it may actually keep going down for a little while. And that's just because I'm pulling on the far side, or I'm measuring on the far side all the way opposite from where I'm pulling. And that ensures that if I'm seeing 300 microns here, it means I have much less than 300 microns on the other side of the system that I'm pulling from. So that is evacuation. And for installers, this isn't the full science of it, but for installers, this is really all they need to know. Check your oil, change your oil, make sure your pump can pull down, use big hoses, remove your cores, connect your micron gauge at the furthest point of the system. Best practices. Now, I see I have Steve Rogers here. Steve Rogers is the airflow master, the airflow maestro. And so he's watching me. He's making sure that I'm not going to say anything stupid. And so I'm not going to say anything stupid. I'm going to keep it really simple. I'm going to keep it practical for what you need to know in the field when you're setting up new equipment, when you're commissioning new equipment. So this is once you already are going to start running the equipment. And I'm going to tell you what I think is most important for modern system. And the first thing to recognize is that a lot of the conversations that are had about air conditioning equipment and airflow relate to systems that we really don't install anymore. And again, I'm talking mostly about residential here, mostly about air conditioning when we're talking about airflow here. But most of the equipment that we put in today has an ECM blower motor in it, electronically commutated motor. Okay. And what that means is that is essentially a variable frequency drive motor that can speed up, it can slow down, so on and so forth. Now, not all of them are created equal, so there are no absolute rules about this. In some cases, you have manufacturers who put in very undersized blower motors. Sorry for some of you manufacturers out there, but when you look at the design specification, the design static for a fan coil, for example, an air handler, and it says 0.2 static, external static that it's designed for, that means that they put an undersized blower motor in the thing. And they did it so that way they can get an efficiency rating, or they could build it less expensively, but that's not the best way. I want to see fan coils with a rating of at least 0.5, and a lot of furnaces are going to have a 0.8 total external static rating. Now, that went over some installers' heads. Obviously, if you are going to be commissioning equipment, step one is you got to have a good manometer. So you have to have a manometer. You have to know how to use it to measure total external static. So here's a practical airflow setup. Practical airflow setup for most installers across the board is going to be to have a good quality manometer, some hoses, maybe some static pressure tips, but on residential equipment, that's not even that important, frankly. But this is the setup that you need to have. that's the tool that you're going to be using that some of you may not have. And this is why I hammer with my installers. Make sure that you use your manometer, make sure you measure that total external static pressure. Now, you've got to know a little bit about the equipment you're working on. And the first thing you got to know is what type of equipment are you working on, because that's going to dictate where you put your probes. If you're working on a gas furnace, then your probes need to go, your positive probe needs to go above the furnace, in between the case coil and the furnace, and then in between the furnace and the filter. That is a standard setup for a furnace. On a fan coil or air handler, then you need to measure on both sides, supply and return, basically, because most air handlers, and again, this varies a little bit whether filter's included or not included, but on most air handlers, the factory filter is part of the air handler assembly. When I say most, I don't know. It's not like I've sampled all of them, but the ones I've seen. And so you have to pay attention to the specifics of what that particular product is rated for. But in general, and this is the general rule that we use, you measure at the top and bottom of what comes in the box. So in the case of a furnace, what comes in the box is just a furnace, right? Your blower and your furnace. You got a separate box for your filter. You have a separate box for your coil. And so you're going to measure below the furnace and above the furnace. In the case of a fan coil or air handler, what comes in the box, you already have the coil. It already comes in the box, right? Your blower comes in the box. Your heat strips sometimes come in the box. Sometimes they're rated for them, sometimes not. And the filter often will come in the unit. And so that's how that unit was probably rated, based on what comes in the box. So you measure above and below the air handler. And the key distinction there is that fan coils, air handlers include the coil, where furnaces exclude the coil. Again, most manufacturers kind of figure for this, which is why often fan coils aren't rated for as high a static pressure as furnaces are. Furnace manufacturers know somebody's going to slap a coil on top of that thing, and that's going to make it tougher for it to work right out of the box, because you're going to have to account for the static pressure drop across that coil, which can easily be, 0.2, in some cases 0.3 inches of static by itself. Those are all factors. You got to know something about the equipment you're working on. That's a big ask for a lot of installers. And that's why I would suggest management teams communicate really clearly about what the targets are for a particular piece of equipment before it goes out. So that way installers aren't expected to sit there and read manuals, because the fact is it's a pretty rare installer who's going to want to sit there and read a bunch of manuals. And this is an area that as an industry we need to grow in. When that installer goes out there, they need to know what measurements they need to be taking and kind of what their targets are and how to use their tools without having to do a bunch of reading if you want them to be successful, which means that we're going to have to do the reading. We're going to have to send out the guides that are specific to that piece of equipment if we want them to be successful. You got to know your target CFM. This is this kind of gets to be woggly ground when I'm talking with a real serious scientist, because even my friend Alex Meany, who's the trainer for RightSoft, really smart guy, he'll say, there is no fixed target CFM. And that is true, but you have to know what you're looking for, at least in your market. What is your general target at design conditions? So in Florida, our design conditions, of course, are based on, just sort of your standard AHRI conditions. But what are we really trying to hit? What target are we really trying to hit? And the target is, we're trying to get it to be 75 degrees inside on a 93 degree day, in that range. That's pretty typical. 95 degree day, we'll round to 95. So 75 inside on a 95 degree day, that's a good target. But we also have to do this thing, called dehumidifying. And so we know, just kind of based on the equipment that we face and what we work on, that we really need to hit about 350 CFM per nominal ton. And we say nominal ton because, if you have a system that's designed to produce nominally 36,000 BTUs, is a 3-ton unit, well, it's not necessarily going to produce that in actual real conditions that we face. And even out of the box, the manufacturer may even cheat that a little bit, and it may be more like, 33,500 or something like that. So we use 350 CFM for multiple reasons, one of which is that we want better latent control. So we want colder coils, but also because the equipment isn't actually producing 36,000. It isn't actually producing 12,000 BTUs per nominal ton. So we say, okay, in general, our targets are 350 CFM per ton. That's what we say in Florida. And if we want to be more accurate, we would drill that down for the specific design of the particular home we're working on. That would be great. And that's a thing we can all work towards, but let's at least just start with saying, okay, what is our target here? And so if it's a 3-ton system, our target's going to be 1050 thereabouts. And so we got our manometer out. We know our target's 1050. That's where we start. The next thing is, we said, become familiar with the particular model. What is the target total external static? What is the design or tested total external static for this particular model of equipment? You got to know that, because you need to be there or below that target on your total external static if you want the system to operate as specified. And that's a key thing there. So if you have a system, and we've seen them, fan coils that are rated at 0.3 total external static or 0.2 total external static. That means that if you attach that thing to ductwork or filters or any other, external pieces, and you are higher than that number, total external static measured once you're done, that doesn't necessarily mean the equipment's not going to work. Depending on how extreme it is, it may work and it may be on the chart of operation. But what we know for dang sure is it's not going to be as efficient, because when you place an air handler, a furnace, a blower under higher total external static, you are going to, in order to do the same amount of work, in order to move the target amount of air on an ECM, because most of what we're working on nowadays, because again, remember, this is install practices, this isn't service practices. Most of what installers are facing today are ECM blowers. It's going to produce that target up to a pretty extreme range. You're going to generally have to get to about 0.7, 0.8, 0.9, 1 inch of static before they stop producing what they're supposed to produce. But they do it at a cost, and the cost is noise, so the blowers get louder. The cost is efficiency, so they become more expensive. The cost is heat. That those motors, as they're having to run faster, as they're having to ramp up in order to produce the same target, in order to reach that target, they're going to generate more heat. So they become more and more inefficient. Potentially, you're going to damage the motor. Caleb says, "Oh, they're going to overheat." That can potentially happen. We had the old issue with the old train systems, with the early ECMs, where they would just blow themselves apart. The blower wheels would just fly apart on them. So there's lots of reasons why we want to hit a CFM target. So that is volume flow rate of air that we pick. And again, I understand my purists out there say, well, that's a moving target. I get it. But for installers, let's keep it simple. Target cubic feet per minute and a target static pressure to stay under. Those are really the two things an installer needs to know. Let's be really honest. Those are the two things an installer needs to know. Then they set up the settings, the wiring, the pin settings, the thermostat, whatever control they're using, they set it up in order to achieve that. And then the duct design, the filter design, all of that supports that static pressure target that we're supposed to hit. So the settings, pins, all that sort of thing, that supports the target CFM. And at that target CFM, we need to make sure we're not going to exceed or hopefully stay below the static pressure design target for maximum efficiency, longevity, all that sort of thing. All right, good. I'm glad everyone agrees with me. So next thing is my green screen acting funny? Yeah, I'm not actually looking at myself. This isn't really a green screen. This is a feature in Zoom that just allows me to choose a background. And so you can see things disappear and reappear and all that. It's kind of goofy, but it's better than looking at my weird office. So from a practical standpoint, choosing filters wisely is really important. That's not generally the installer's responsibility to choose the filters, but it is a really important part of the process. And sometimes they may have some say in that. And generally speaking, we're putting in filters that are too restrictive. I mean, it's just that simple. If we're putting in 1-inch filters on most equipment nowadays that's over MERV 8 or over, it's probably too restrictive unless we're doing filter back returns and you got nice oversized filter back returns. From a kind of overall design advice standpoint, we've been doing this. I did it at my dad's house. Neil Comparetto does this all the time. John Semmelhack designs for this. Really big, oversized filter back returns with 2-inch or larger filters work really great. I mean, I did my dad's house. We have vastly oversized direct returns going to a 5-ton unit, and his return static is essentially immeasurable. It's, under, I think I was measuring 0.01, something like that, return static, something, in those lines, very, very low return static. And that's a good thing for most equipment. It's not, a lot of people will say, well, you can get too low. On a return, I think you're limited by only how big of ductwork you can fit on the equipment. If you're running it through an attic or a hot space, something like that, people will talk about gains that can occur due to load velocity, but ACA talks about that in Manual D. So anyway, the point being that, sorry, I got off there. Choose your filters wisely. Go with larger surface area, less restrictive filters, if at all possible, even if you have to do some exotic designs in order to get those things in place. Next thing is, for an installer, visually inspect ducts, blower, settings, and wiring. This is on the changeout side, because a lot of times in changeouts, they're just slapping it in on existing ductwork. Those have to be visually inspected at very minimum. Obviously, it would be better if we were using the duct blaster system to actually test. See there, Steve, trademark of the Energy Conservatory. If you're using duct blaster to test, that would even be better, but doing visual inspection at bare minimum is the best thing to do there. And then checking your settings and wiring is so big. It's It's the part that if a installer doesn't know how to do this properly on the piece of equipment they're working on, it just results in this huge cascade effect. Because if they set a system up to airflow that is too high, for example, they're going to be measuring high static and they're going to think they have a ductwork problem. If they set the system up for an airflow that is too low, and again, this comes down to, pins, dip switches, whatever the particular equipment is, you have to know your heating, your target heating and your target cooling airflow, and you have to make sure that the pins and everything are set to actually achieve that. Because if they set a target that's too low, or say they have a dehumidification terminal and it's not energized, so it's in dehumidification mode and running a lower fan speed while they're testing, or it's running, they only have a Y call versus a Y2 call, and so it's only running 60% of its designed airflow, they're going to see low static and they're going to think that the system's working good because they see low static. But you have to hit the target first. So we have to make sure that installers are trained appropriately on how to wire and set up this equipment. When you go to ECM 3.0 equipment, that's more the settings on the actual controller thermostat that matters versus the way it's wired. If you just have those simple 2-wire or 4-wire setups, you're not doing those settings in the equipment itself. You're doing it at the control, but making sure they know how to set those up. And frankly, it's getting to the point where some of these commissioning tasks are maybe best done by somebody who's kind of qualified to do that part after the fact, just to go in and test again. But if our two tools in our bag here, or really our one tool, is just our manometer, then the two things we have to make sure that are correct are airflow and static pressure. And if those two things are correct, then we're going to be doing pretty good. In fact, we talk about fan tables a lot, referring back to fan tables. Fan tables are used a lot on PSC motors in order to kind of dial in your airflow, set your fan taps. On ECM, really all you have to do, look at the design, total external static, make sure that you have the proper airflow because everything is set up properly. Now that's a big if, right? And when it comes to validating airflow, purists would say, if you don't know exactly what it is, who's to say that control's set up properly? And it is true. But at that point, really truly measuring air velocity for an installer is generally going to be over their head. If you have a true flow, that's actually the best way of doing it. And an installer can do that. Still just a touch mathy, depending on the manometer that you have, that you're doing it with. But true flow is probably the most practical way of doing that. And we do have some true flows at Kalos. Honestly, we don't have them on every installer's truck because, again, installers, it's limited what we can expect them to do. But I would always start with the manometer. Visually inspect, measure total external static pressure in the right spots for the particular equipment you're working on. Test dehumidification mode if that's something that you have wired up. In our market, that's really big. Depending on the different stages, if you have, a high fire, low fire furnace, test low fire, test high fire, test stage 1 cooling, test stage 2 cooling, test dehumidification mode, make sure that it ramps up and down in all of those cases. And once you have kind of a baseline on your manometer, well, now you can easily see when you're increasing and decreasing airflow, because as you increase airflow, your static pressure will go up. As you decrease airflow, it will go down. Now, you're not necessarily going to know what the airflow is unless you reference the fan charts or unless you're a mathy person. But I think for a standard installer, that alone is a really good place to get them started. Knowing the equipment, hitting targets, measuring static, testing the different modes, and watching the static go up and down appropriately as they change modes. That's my advice there. That's practical airflow setup. This is an example of a MERV 11 filter from a very well-known brand. This is a 16 by 20 filter, I think. And so on a 16 by 20 filter, if you're just moving 820 CFM, this alone has a 0.33 pressure drop across it. It just shows you how a lot of the out-of-the-box air filters that we're putting in equipment are major, major problems with the equipment. And so choosing filtration is just as big of a factor as duct design in my book, and sometimes even more than that. So design your ducts properly for sure, but also make sure you're setting people up to succeed with the air filter setups that they've got. Just because the filter fits doesn't mean it isn't restrictive. This is a picture from Neil Comparetto showing the pressure drop across this filter. 0.82 pressure drop. Again, just because a filter fits underneath an air handler doesn't mean it's the right filter. It doesn't mean that is even just because you put a filter rack under a piece of equipment doesn't mean that that's even the best. Even with 4-inch filters, we've seen this. You got a 5-ton air handler. Those are the worst. 5-ton furnace, because they are moving, potentially 2,000 CFM of air, cubic feet per minute of air. And so you really are going to need an oversized filter setup for a system like that. Design total external static pressure isn't always 0.5. It does vary. It could be 0.8. It could be 0.2. It could be 0.3. And you got to make sure that when it's all said and done and the thing's running the maximum target airflow that you're going to run it at, that you're going to be below that target. 400 CFM per ton isn't always right. Some markets you need more. Some markets like ours, you need less. And also recognize that tonnage is kind kind of a moving target too. So tonnage is a nominal number. So a 3-ton system doesn't always produce 36,000 BTUs. And that's something that you gotta have in your grasp. Now, again, for an installer, they just need to know that there's like a couple different layers of knowledge. Point number one is just to know that it isn't always the same. But honestly, asking an installer to figure out what the math is for a particular install, I think that's a mistake. It needs to be done in the sales and management and commissioning side of things, where they need to know the targets they need to hit and how to hit them. And then they can be expected to actually do that part of it, depending on the skill of the installer. But asking them to do a bunch of complicated math, not something I would suggest. Again, I keep saying that, but we want to set people up to succeed. And then finally, measuring airflow accurately is harder than you think. And, Steve and I and Bill Spone and others have talked about this a lot. Measuring airflow accurately is really hard. Getting a number on a tool that tells you this is what it is, that's easy. But it being anywhere near correct, that's hard. Which is why I say start with a manometer, start with understanding your equipment and your targets. And I think that's going to be, and then kind of fall down the rabbit hole from there as you learn how to properly measure airflow. Because again, we're in a market where almost nobody is properly measuring it. A lot of people talk it, very few do it well. And so starting somewhere is what I'm suggesting here versus trying to get perfect with it, because a lot of people get, I want to say, disenfranchised. They get frustrated with measuring airflow and they give up on it. Estimating airflow is easy. Measuring airflow is hard. That's what Ed says. Very, very true. Very true. All right. So this quickly is showing you an FB4C carrier. This is showing various taps at different static pressures and the airflow that it produces. Yeah, you can pretty much tell this is an ECM motor because you don't have these massive drop-offs actually, I can't say that this is ECM. I don't know if this is ECM or not, because it is definitely consistently dropping as you go. But as the static pressure increases, you see that there is a decrease in airflow. And again, this is just an example of a fan table for a particular piece of equipment. I should have definitely known whether or not this is an ECM motor or not. So I need to do better on my slide there. Next thing is with airflow, I would definitely suggest installers using MeasureQuick, not because it's the only way to do it, but because it's by far the easiest way. The airflow that you get in MeasureQuick is an estimate based on some system data. But if you're connecting in all the probes that you're supposed to be connecting, return side enthalpy, supply side enthalpy, suction temperature, liquid temperature, and your pressures, it's going to give you a pretty good indication whether or not the system is in the green zone. Again, it is an estimate. This is not measuring airflow. For sure, it is giving you an estimate. But for an installer, as part of a commissioning process, in addition to knowing your target CFM and measuring static pressure, I think this is a really good additional check to say, is my airflow in range? And this kind of is based on the theory that, it's not a theory, it's a fact, that if your airflow is wrong, that your system is going to have a really hard time operating within the design targets as far as enthalpy delta, pressures, all those sorts of things. It's going to be very hard for a system that doesn't have proper airflow to work right. MeasureQuick is a great way of doing that, and it is something that we do at Kalos. That's it for airflow. We're going to move on now to preventing compressor problems in the last 13 minutes of this presentation. Preventing compressor problems. First thing is, even Cary Grant learned that a digital manifold is the way to go when it comes to accurate measurement of superheat and subcooling. Preventing compressor problems. I would say that one of the biggest challenges that exist with compressors is due to, first of all, improper evacuation. That would be the number one thing. So I already talked about that, but getting that atmosphere out of the system using best practices for evacuation. That's number one. But the next one would be compressor overheating. And the compressor overheating is due to suction line temperatures that are too high or refrigerant densities that are too low. Simply, what that means is if you have suction pressure that's way too low, that could be because you have a plugged expansion valve. It could be because you're undercharged. Or if you have suction line temperatures that are too high, even if your mass flow rate is correct, both of those can cause your compressor to run hot because a compressor is refrigerant cooled. It says it right here. You know it's true because it says it right on the slide. Compressor is refrigerant cooled. We need to make sure that we're returning the proper temperature and density refrigerant to that compressor in order to keep it cool, which means that our suction pressure needs to be within the zone of what it's designed for. And our suction temperatures generally need to be below 65 degrees. Now, that number isn't one that I just pulled out of my rear end. That pretty much comes from all of Copeland's literature. We need to keep suction temperatures below 65 degrees for normal operation. Key thing here is that these systems are designed, and especially, properly made, to handle a lot, because they have to be designed for hot pull down. Hot pull down means you have a space or a box or whatever that got warm and now you have to cool it. And when that occurs, that is kind of a worst case scenario on a compressor because your suction temperature is going to be high. We recognize that during hot pull down, there's going to be cases where your suction temperature is above 65, but when it's operating, we want to have a suction line temperature at the compressor that's below 65 degrees for proper cooling. Some common things that cause too high of suction temperatures would be, improperly insulated suction lines, really long suction lines. Cases in Florida where we run suction lines through a chase pipe with the liquid line and we don't insulate it properly. Those are all cases. Running it through a super hot attic, that can cause it to be too high temperature. And then finally, just having high superheat in general, having a system where the superheat isn't set properly, maybe it's undercharged, maybe the valve, if it's a adjustable TXV, is set improperly. But compressors are refrigerant cooled, so they need to have the proper mass and they need to have the proper temperature of the suction gas returning. Another cause of compressor failure is flooded operation is actually less common in most residential applications than flooded starts. So flooded start is where refrigerant migrates into the compressor crankcase, and when the compressor starts up, that refrigerant starts boiling and it foams the oil and the oil gets thrown out of the compressor. It's really bad for it. And so flooded starts, there's several things that can help with that. It depends on the application. The manufacturer is going to tell you what to do. But crankcase heat, so when that compressor, especially when it's off, it's heating that sump of that compressor to keep refrigerant from condensing inside that around the compressor, and it helps prevent refrigerant from condensing inside the compressor when the system is in the off mode. There's also things like liquid line shutoff solenoids that prevent it from migrating, and even hard shutoff TXVs, which are pretty much ubiquitous nowadays. Those can also help. Preventing compressor problems, also using factory hard starts when required. That is another thing that we see a lot. People fail to put in the factory hard starts when they're supposed to have them in long line applications. And what happens is, if you don't have the factory hard start when it's designed to have one, is sometimes it won't start, especially when it's attempting to start under pressure, and that causes it to go out in thermal overload, and that can cause long-term problems if that thing's going on and off on thermal overload quite often. So there's just a lot of factors especially when you have long lines, and you need to pay attention to those long line factors. Some cases they're going to recommend, solenoids, and some cases they're going to recommend hard start kits, and you got to follow those recommendations. We see those get ignored a lot on a lot of equipment. The next thing to prevent compressor problems, again, these are sort of installer considerations or install level considerations. The next one is to weigh charge in and out. It drives me crazy when I see guys look at their pressures, especially on startup of new piece of equipment, and their pressures don't look right to them. And so they start adding or removing refrigerant without using a scale. When you use a scale, you have a much better sense of whether or not something else is wrong, because you've measured your line set, and you figure out, okay, well, I need to add half a pound. I need to add 6 ounces, whatever the case is. And then you add the 6 ounces or the half a pound, and it's still not working right. Well, now you don't add another 2 pounds. But I've seen cases where installers put 6 pounds of refrigerant in the system because they don't have a sense of how much is going in if they're not using a scale. And the same thing is also true of weighing it out. So weighing in and weighing out is such a big factor when you're charging or recovering from a system. Preventing flooding with proper superheat is big, and it's not just big with fixed orifice systems. I mean, the amount of fixed orifice systems that are coming out nowadays are less and less. I don't think we install really any piston systems, fixed metering device systems anymore. So setting superheat by charge isn't as big of a deal as it is checking it to ensure that the TXV is doing what it's supposed to do. And you will see cases where a TXV will flood back when the bulb isn't properly mounted, isn't firmly mounted on the suction line. And I see some systems come out of the box with loose bulbs or bulbs that aren't insulated that have low superheats. So if you out of the box have a system where you're measuring below a 5 degree superheat at the evaporator coil and really below a 10 degree superheat outside, that means that valve is overfeeding a little bit. And so you want to check that bulb and maybe insulate the bulb or make sure that it's nice and snug on the line, especially if it's been field installed. So in cases where you have field installed valves, that's where you see more and more of that. Keep in mind that as far as the compressor is concerned, it's the suction line temperature outside that matters, not what it is at the evaporator coil. As far as the TXV is concerned, it's the suction line temperature inside or the superheat inside that matters. So you have this kind of, conflicting thing here where the compressor cares about what the suction temperature is coming into it because that's what keeps it cool. But the TXV doesn't know what the temperature of the suction line is coming into the compressor. It just knows what the suction line temperature is, the superheat is at the outlet of the evaporator. So that's why understanding the difference between compressor superheat and evaporator superheat is a pretty significant thing to think about when you're doing this. Keep in mind that from a compressor standpoint, airflow issues cause many problems. So if you have low airflow inside, that can result in you having flood back to the compressor. That's the most common, where you have liquid coming back to the compressor, especially on fixed metering devices. That can cause that. But even without fixed metering devices, you can have cases where low airflow causes a low suction density. So you can have examples scenarios where you may even have appropriate superheat per se, but because you have low suction density, you can still run a hot compressor internally. The other factor there is oil return, especially in older systems. With POE oil, it's less of an issue, but when you have low suction velocity, meaning low pressure coming back to the compressor, you have lower suction density, it's not going to carry the oil as well. So low airflow causes lots of problems. That's why we talk about airflow, and then also checking the voltage under load. I talk a lot of technicians are really obsessed about measuring amperage, and measuring amperage on a compressor on a system, that is a good thing to do. But when you ask the question, how many times do you make a change on a brand new system because of what the compressor amperage is? Well, the answer is never. You measure it, it's below the rating, you move on, right? But there are cases where voltage can be an issue. So checking voltage under load is a really big thing, both for over voltage conditions, which we're seeing more and more power companies giving us voltage that's too high, and also cases where the voltage is too low. So measure that voltage at the compressor under load to make sure that you're delivering what you're supposed to. So while the system is running, measure the voltage, especially going into the condensing unit with a voltmeter. That will help prevent compressor problems, especially on more modern systems where you have inverter-driven equipment and that sort of thing. And that is it. So some valuable resources, of course, hvacrschool.com, Measure Quick app. Always suggest using the Measure Quick app. Copeland mobile app. Copeland mobile app is incredible, especially if you're working with Copeland compressors. You can find the exact specifications for a ton of stuff and also test compressor performance with the Copeland mobile app. The refrigerant slider app from Danfoss is my favorite app for kind of like a online PT chart, just an easy to use PT chart if you're working with different refrigerants that you're not used to. And then finally, the Johnstone app is an app that I use a lot. And that's because we do a lot of business with Johnstone. So hopefully you found that helpful. I appreciate you all for taking the time to watch this, and make sure that you do not kill systems by following these best practices. Just to summarize, I'm going to go all the way back to the top. Make sure that you're brazing properly, flaring and leak testing. Make sure you flow nitrogen. Make sure you're evacuating properly, getting all the air out of the system. Make sure that you're pulling below, we suggest below 300 microns, and making sure you don't decay to above 500 in 10 minutes. Don't forget to set up the airflow, hit your targets, check your static pressure, and prevent compressor overheating and flooding. All right, that's it for today. Have a good one, guys.